into it. So I'm just setting the stage because Shri and Kritika are gonna go into much more depth than we did, but we're just really happy that he finally gets his day in the sun. I've got all the kit on, just trying to give him some love. And this is Numi, and now he gets to watch the first ever Numaproj uh, talk and demo at KubeCrash. Thanks, Shri. Thanks, Kritika. I'll let you all introduce yourselves with your slides.
Awesome. I hope everyone can hear us, and thanks a lot for thanks a lot, everyone. I hope you are enjoying CubeCraft today. So I am Shri. I'm part of the Intuit platform team. I work as a product manager on Numaflow, and I have Kritika who is joining us to share about the platform as well. And our topic for today is primarily around how we are actually using Numaflow for doing inference on streaming data and some of the challenges and that we have observed it into it while operating at scale, and then how did we go about solving them using Numaflow. So with that, here is our agenda. Like quickly, I'll share about what Intuit does and how the platform works at Intuit, and then some of the problems that we have specifically seen around like stream processing in the context of AI, the challenges that the teams have observed, and then how Numaflow went about solving for all of those. And then we'll do a quick demo. Without demo, I don't think any talk is not yet done. So with that, moving on. So as majority of you might know, Intuit is a global fintech company with products like TurboTax, Credit Karma, QuickBooks, and Mailchimp that we might have used either for filing taxes, or if you are actually running some of your small and medium businesses, you might be have using QuickBooks for accounting needs and bookkeeping and all of that. And you can see some of the scale that we operated, where we have like close to 100 million customers, processing around like more than $100 billion in consumer tax refunds, and then processing close to $2 trillion in invoices, and also running payroll at scale. So if you look at all of these different kinds of products, right from consumer products to even on the enterprise side, we operate at scale, and all of our products actually run in a cloud native fashion on Kubernetes. So when you're running at this scale, like definitely we would be using a lot of open source products. So one is, of course, we have been a big believer of open source products, either as a developer or contributing back to the community, or even end users of different open source projects as such. So like we have been awarded with end user awards from CNCF in 2019 and 2022, and you can see some of the projects that were developed and open source by Intuit. Like the biggest one that almost everyone in the Kubernetes ecosystem would know of is Argo. From some of the learnings that we have had with Argo and Argo workflows and Argo rollouts is where uh, we have come up with a new project called as Numaflow, and like we are going to talk specifically about Numaflow later today. So with that, let's try to move on to the what is our problem statement or the topic for today's conversation. Like we are going to discuss about stream processing for AI and ML in day to day. So like what do I mean by stream processing? Like the first and foremost is like there will be a lot of events happening across the board. Either if you think about let's say for example you're trying to purchase products on Amazon or different kinds of e-commerce websites, like you would want to understand what the user behavior is, and then accordingly provide some kind of recommendations as they are happening. You would also see the similar kind of examples on even on the platform side, where if you're doing some kind of observability or monitoring or any of those, like you want to understand or process events as they happen, and then try to respond to based upon the events, like and respond accordingly to based on the events that as they're happening. So like let's take some examples. Like you would look at stream processing, or you would see stream processing on a day-to-day basis, like for different kinds of, especially in the context of AI and ML. The first and foremost is like feature engineering, like the way I mentioned, right? As the events are happening, you would want to enrich your data, you would want to process them so that you can calculate some of the features, and then you can actually feed it to your model so that you can do some kind of inference. The second is like the inference use case in itself. Let's say you have processed all of this data, and then you want to do inference. Let's say you are making some kind of, or users are making some kind of payment transactions. Like are these fraudulent transactions or not? That's like inference at real time on the streaming data as the events are flowing in. And then lastly, you would also want to have the latest and the greatest of the data feeding into your training pipelines and for your models to train upon. So that's like the third use case around the training. So in short, like you would see this entire closed loop as such of stream processing on a day-to-day basis in the context of AI ML, right from like feature engineering to inference to training across the board. So you can think of it as like stream processing is like a backbone of AI ML, definitely. So let's dive deeper into some of the challenges that we have observed. So in the past, stream processing has always been something like done by data engineers. Like, what do I mean by that? So when you think about in the context of stream processing, there's like two parts to it. One is you'd want to understand the stream processing concepts, like as the events are happening, you want to process them, either trying to learn about windowing, reduce, map, and all of those different concepts as such. And then the second aspect of it is like majority of the frameworks are primarily like Java or like Scala based as such. So that was some of the biggest pain point for some of our teams, specifically not just the ML teams, even on the developers as well, because stream processing is not just bounded for like data engineers as such. It is something beyond, yeah, like data engineering. It could be for developers would want to use it, or maybe our ML teams would want to use it. So like when you think about different personas coming into play, like you having only a Java based framework or like something that is very deep rooted into data engineering itself is not going to fly as such. So that is one of the pain point that we have observed, where people wanted to have a stream processing capability or framework that is beyond Java as such, and that is very easy to understand and go about doing things. And the second is like teams were actually spending a lot of writing boilerplate code. Like, what do I mean by that? When you think about all of this stream processing as such, like first you need to receive all of these events from like different sources. It could be some of the prominent tools that you would tend to use are like maybe messaging queues like Kafka, or maybe Pulsar, or different kinds of messaging systems or queues and all whatnot, where you would want to receive all of these events. And then finally, once you process them, you want to send them downstream as well. But a lot of our teams are actually spending a lot of time in writing this boilerplate code. Like if I'm a developer or maybe an ML guy, like why should I really spend a lot of time in writing these integrations again and again whenever I write these new pipelines or consumers or like whatnot? So, and on top of it, there is also another problem where some of the teams may not be really implementing them efficiently, leading to not efficient consumption, leading into like consumer lag and like different kinds of manifestations of the same thing. And then lastly, they were also spending a lot of time around scaling. Let's say, for example, like majority of us know, especially on Kubernetes side, the most prominent autoscaler we tend to use like is HPA, where probably you'd be looking at like CPU or memory utilization metrics, and then try to scale all of your consumers as such. But when it comes to scaling your event consumers or like stream processing pipelines, ideally you would want to scale them by looking at let's say like how many events do I have pending in my messaging systems, and accordingly scale of them. And also it also depends upon your downstream and at what rate you are processing and all of that. But that was some of the pain points that the teams had, was like where they were spending a lot of cycles and either statically hard coding the pod count and all of that so that you don't have any consumer lag, or they were doing a lot of what do you say, like dry runs and performance testing, trying to figure out what is the ideal auto scaling as such. So either it's like manual or probably static auto scaling that they were trying to do, but teams were actually looking for a solution which would do auto scaling end to end, right from looking at like, hey, how many events are pending, at what rate am I processing, and like at what rate is my downstream able to consume. So with all of these challenges in mind is where we actually came up with this new platform called as Numaflow, primarily solving all of your stream processing challenges, not just in the context of AI ML across the board. It could be simple event consumer use cases, right from there to all the way till AI ML or any kind of real time data processing use cases that you might have. With that, I'd love to hand it over to Kritika. She's going to share a lot more about the platform, how it works, and also a quick demo as well. With that, over to you, Kritika.
Thanks, Shri, for a very detailed explanation of the problem statement as well as the challenges faced by most of the ML engineers. And hi, everyone. This is Kritika, and I'm a staff software engineer at Intuit, and I work with Shri on the platform team. So what is Numaflow? Numaflow is a serverless platform for stream processing. So first and foremost, what we do is we abstract infrastructure. So by this, we enable ML engineers to focus just on their stream processing or inferencing and eliminate the need for them understanding the underlying infrastructure, in this case being Kubernetes. All they have to do is we make sure that the platform itself is very familiar with the language that they are going to write the streaming or inferencing in, be it Python or Java and so on and so forth. Secondly, we also decouple the ML logic from sources and sinks. We realize that ML engineers are focused largely on the payload or on the data, right? And they don't really care about where they are reading the data from. Is it Kafka, or is it Pulsar, or is it HTTP? And what they are doing with the data once it's being inferenced. Is it being written back to multiple sinks like DBs or Kafka again, and so on? So we decided we'll provide built-in sources and sinks for these purposes, and all the ML engineers and users have to do is focus on their inferencing and processing logic. Last but not the least is we also provide a very scalable, reliable, and secure platform. As Shri mentioned, we noticed most of the users and ML engineers were actually hand tuning pod counts and scale counts depending on the data. I mean, depending on the traffic that was coming in. Like most cases, what happens is early morning there is a lot of traffic coming in, and late night there's not a lot of traffic coming in. So we decided the platform is responsible for scaling up and down based on the data that's coming in, and not necessarily something that the user has to do to tune to avoid consumer lag and things like that. Moving on. So, how does a Numaflow pipeline actually look like? So, here you see this is a directed acyclic graph, and it's composed of two different components, right? It's vertices, and they are all connected by edges. So, the first thing that you see here is the source, where you're basically reading the data from either be it Kafka, Pulsar, and so on. And this is something that the ML engineer or the data engineer does not have to focus on because it's provided built in by the platform. The first part is this UDF, which is the user defined function, where we are writing the inferencing logic, the pre processing or post processing logic, or training, or anything that you want to do. In most cases, we have also noticed that our users want something like conditional forwarding. In the case of low cardinality data, you might want to run against particular models, whereas in the case, if you let's say you have very high cardinality data, you may want to do something else. So you have a path to diverge based on the feature that's coming in. And last, we also persist the data into different sinks. In this case, it's written republished back to Kafka, or we also write to blob stores or databases and so on. And so that it can be consumed by downstream system, and further personalization can be done on the data. Moving on. So now let's time to do a quick demo. So we're going to actually do image recognition. We're going to send in an image, and we're going to see what a description of the image being printed out in the logs, right? So let's. Oh, sorry. Actually, before that, yeah. So how does the pipeline actually look like? Right. So first is the source. Receives a stream of data that you can see here. The next is the prediction vertex, where we are actually going to do a prediction on the image, or we're going to recognize whatever the image that we're going to be sending, and also going to provide a description of the same. And finally, there is a sink where you're going to log the results to. As mentioned, Numaflow comes with a large number of inbuilt sources and sinks like Kafka, HTTP, Pulsar, log sinks, and so on. In this example, I'm going to be using an HTTP sink, which means I'm going to post data to an HTTP endpoint, and we're going to be writing the results to a log sink. Numaflow also has, the capability to write your own sources and sinks as well. Like we have SDK support in multiple different languages, so some users even choose to write their own sources and sinks. The prediction vertex here, you can see, is actually just we are hosting an LLM model through VLLM, and in this case, it's hosted locally on the pod itself. And you can see that the image that we're going to send is like a dog in a Halloween costume, since it's like a Halloween season. Yeah, now let's quickly go here. And yeah, I already have my port forward and everything running. So what I'm going to be doing is I'm going to be making a post call. And so I've sent the data through. And now, okay, so this, you guys can still see my screen, right? Yeah, cool.
Yes.
Yeah. So this is Numaflow comes with a bundled UI, which means that the UI not only gives you it not only tells you how the pipeline actually looks like, in this case like an HTTP source, or the prediction vertex, the inference vertex, and the log sync. It also gives you much more details about what what is the CPU memory associated with it, how many pods is it running, and other matrices. And you can also see the logs associated with each container in the pod and so on. Here in this example, you can see in the log sync, it's just like at this particular 1913 UTC, I just sent in an image. It says a cute dog dressed as a witch surrounded by pumpkins and a bat logo. Now, let's say I send in another image, right? I'm going to send like a pumpkin man image, and let's see that image come through as well. So yeah, you should be seeing the log. Yeah, a person dressed in a suit and carrying a briefcase with jack-o'-lantern head walking through a parking lot. So yeah, this is a simple pipeline which is unidirectional, which means it has a source, a prediction, and a sync vertex. We look at more complicated pipelines as we go along, but this was just to show you how the UI looks like and what are the features it provides. Now going back, yes, to the slideshow. Yep. Yeah. So how does a Numaflow pipeline actually look like, right? Like how does the declarative syntax of defining a Numaflow pipeline look? So as you can clearly see, this YAML is what defines a pipeline. It's a DAG. It has two major components, the vertices and the edges. So you can see the three vertices that are here, the source, which is like the in vertex, the HTTP source, the inference vertex that you see here. And here you also have the ability to provide more resourcing to it as and when you need it, like you can provide CPU, memory, etc. And then finally you have the log sync, which is the out, and then the edges here indicate, okay, from in to inference and inference to out is how the graph is connected. We also mentioned a lot about how we don't have to worry about writing the sources and about reading data or writing data from different sources in syncs, be it Kafka or Pulsar and so on. And so here is an example of the piece of code that you will need to write. So all you receive here is, you can clearly see there is a datum object that we are receiving, and all you have to do is do your processing on that datum object. In this case, we are calling an LLM model here, but you can do any kind of stream processing. You can filter data, you whatever you want with it. It's just a simple datum object, has no reference to Kafka, Pulsar, or anything of that sort. It's fairly easy and quick to write these. Going back now, let's look into a more. These are some complex pipelines that you can see. You can have multiple sources, multiple UDFs, as you can see, syncs. These are different combinations. And now let me take you to a complex pipeline that's been running it into it at scale for anomaly detection. So I know that this is probably not easily viewable by everyone, but this is a very it's a pretty complex DAG that you see here with different vertices written in different languages, and it's doing anomaly detection, which means it's basically predicting anomalies on various web services, web components, and services that run at Intuit. So you can see here. So now let me go here. So it's a more zoomed in version that you can see here. You can see that there's an in vertex, which I know is a Kafka vertex. Basically, it's reading data. It's built in. Users just can plug and play this and not have to worry about writing this code. You move along, you can clearly see there is a pre-process vertex. This pre-process vertex is where you basically filter out any data, or remove any data that's too old, or whatever you want to do with it. Then there is inference. Inferencing is here where you do the inferencing or the anomaly detection, make a prediction, and finally write the data, do some post processing, and write to downstream systems like the Wavefront sync and the Kafka sync and so on. We also have the capability in this example. If you see that there's also, you can say you can kick off a trainer workflow in case there's a model that's not found. You can kick off a trainer workflow as such, and then that's being written to another sync to perform the training action as well. So as you can see here, this is a perfect example of a polyglot platform that we have. We do know that the inference vertex here is written in Python because it's easy. More libraries are available to do that in Python, whereas the pre-process and the post-process that you see here are all written in Java and Go, which have more libraries for slicing and dicing data in general. Again, you can also see that each of the vertices here can also show you, the number of pods that each of them are running, so they can scale independent of each other depending on how many messages they have to process. And if you click on each of the vertices, it also shows you like CPU, memory, utilization. Here you can see there's a yellow sign indicating that, okay, it's like kind of approaching 50% CPU that you have allotted, and so on. And yeah, you can also look at the logs here, which tells you, okay, if you're like debugging something, you can clearly say, hey, okay, I received a delete event. In this case, you can see that it says it's a delete event, and so on and so forth. So it's a very comprehensive UI, which not only tells you how the platform looks like, but also pipeline also looks like, but also tells you how to also helps you debug any major and critical issues that you may have. And we know that this pipeline's been running actively for the last 1 year, and it's been used to actually proactively detect incidents and prevent incidents based on the anomaly scores that it generates. Yeah,
Yeah,
thank you.
and one more thing I just want to highlight, Kritika, if you can go back to the
Yeah,
same pipeline,
yeah.
is let's say, for example, if anyone is actually interested in provisioning dedicated resources from for one of your steps, you can definitely do that. Let's say, for example, maybe only your inference steps requires GPU and rest of your steps need only CPU. You can definitely do that. So that is like a way of more isolated and precise allocation of resources for the steps that you only need. That is something that you definitely get. And then also you are seeing that where different teams can come together and work on the same pipeline. So basically you can use like Java, Go, like each of these are individual vertices. Each of them are nothing but containers that are auto scaling based upon back pressure and all of that. And I do see a question which is like on how is back pressure handled if you have if you are decoupled from the source like Kafka. So essentially the way we do back pressure or auto scaling is like we do what we call as like the queue depth analysis right from your sink, from basically right to your left, where we understand each of your steps on how each of them are being processing. And we also the way the data moves between from one vertex to the other is via interstep buffers. We use nats, that's the jetstream by default, and you can also configure any buffer that you're interested. So essentially we know at what rate each of the step is processing and like how much is available in the buffer and all of that. So let's say, for example, in one of your sink is completely down, you're writing to your database and you're not able to write any more events to your database. So essentially what would happen is you definitely see a back pressure piling up saying that, hey, I'm not able to consume any more events, I'm not able to process any more of those events, and a lot of our buffers are completely backlogged. So we'll all together completely stop consuming from Kafka or any of that. So we have absolute control on like when we want to consume and at what rate we want to consume and all of that. And you can also definitely fine tune them and based upon the needs as you may have. And then you can also configure something like, let's say your sync is down, probably you would want to write something like a dead letter queue and whatnot. So we do provide provisions for like configuring a fallback sync and all of that for some of your sync if you have any of those constructs or like needs as such. So that's how we do have how do we handle back pressure and all of that. More than happy to chat a little more, but before we go there, Kritika, do you want to go back to the slides? And I just want to share like how community is also using Numaflow. Go to the next slide. So yeah, in short, Numaflow is basically a real-time or stream processing platform where it's completely language agnostic and Kubernetes native. And if you look at the prior platforms as such, Flink or any of those, they were not Kubernetes native. You might have to use operators and all of that. But here it's like completely Kubernetes native. You can use any language that you would want to use. You can also deploy some of your pipelines on edge devices because we are resource efficient. You can absolutely scale down to zero if you're not receiving any events as such. And I'll also share some of those examples as we go along to the next slide where how the community is using. So Kritika, can you go to the next slide? So here are some of the companies, apart from Intuit using it for anomaly detection, a lot of event-driven application development, all of those use cases. Here are some of the examples that you would see from the community. Let's say, for example, NTT uses it for accelerated sharing, where each of these vertices that we have shown you in a pipeline, they have allocated different kinds of resources for each of those. Let's say, for example, and one of the vertex, they were trying to use FPGA, probably GPUs, and different kinds of resources based upon the need and the processing that you're actually doing in that particular processing step. And Lockheed Martin uses it for like IoT data processing. And one of the examples that I definitely want to highlight is like B-Cubed Engineering. So they actually deploy some of Numaflow pipelines on air-gapped environments on edge devices completely, where they use it for like digital signal processing and some of those needs, where they create a pipeline, deploy it on their edge devices, and then let it go. Like if at all you want to make a change, you definitely have to bring this device out of these air-gapped environments and then try to modify any kind of changes. So essentially that says that like the platform is solving for some of your enterprise needs, like the Intuit, NTT, and Lockheed Martin, all of that. And at the same time, if you have like very lightweight edge use cases where you definitely need a lightweight platform that is absolutely reliable, running on Kubernetes with low footprint, you can definitely use that. So in short, like Numaflow is the one-stop shop for doing stream processing on Kubernetes. Either you have like simple use cases or enterprise use cases, you can absolutely use the platform as such. So yeah, thanks a lot for giving us the opportunity to share about Numaflow with all of you today. Would be happy to answer any questions or anything like that.
Hey there was one in the chat that you didn't get a chance to answer from David Parker. How is back pressure handled if you're decoupled from the source like Kafka?
Yeah, I think, like I mentioned, primarily the way we look at the entire order scaling or back pressure analysis, like as I said, is primarily doing a queue depth analysis, where we understand at what rate each of these steps are processing and how the buffers are being filled up, accordingly considering all of these end to end, right from yes right to your left. And accordingly, if you want to scale one particular, I think while Kritika was doing the demo, you saw that Kafka, I think the source vertex was initially having like 3 pods, and then all of a sudden the processing or the number of events went up, and then the number of pods actually went from 3 to 4. So that's like the dynamic auto scaling that is coming into play, where we are trying to analyze in real time at what rate we are receiving those events, at what rate are we processing them, even by your downstreams, and accordingly do the back pressure analysis, and then stop consuming if at all there is an issue in one of your processing vertices or even in your sinks as such.
Okay.
Awesome. Well, thank you both for being here. It's been great to learn all about Numaproj, and can't wait to see more of what's to come.
Yeah, definitely. And thanks for all. We're going to show Numaproj at KubeCon in Atlanta. And we'll be doing a little, I think, showcasing at All Things Open as well. So if anyone is coming to either of those conferences, there was a Numaproj talk last year at All Things Open. So this isn't the first ever Numaproj talk. It's just that Numi's been waiting next to the orange people for a long time, because this thing has been an Argo love fest for a few years, with all the popularity of Argo in the community. So it was nice for us to show what's next from that incredible team. And I think we can all in the community expect really good things. But also, if you're looking for your next community side hustle, we're always looking for contributions, or come and try it out. We'll work with you if you want to, give it a test run. And it might be something that would work for you. And, we definitely love to get more users and vendors on board, honestly. So super happy. Thank you so much, Shri. Thank you, Kritika. Appreciate it.